right, good morning everyone. So we'll get started. If you just say good morning or hi, whatever in the chat, I will take that as attendance, okay? Let me pull up my screen here. All right, and let me see. To full screen mode here. Okay, so to start with, again, a few reminders here, list over here about homework to use, and then schedule for finals, okay? And then lab this week is law of reflection and refraction, okay? So about half of you guys have done that, all right? And the rest of you guys will be doing it this afternoon. So let's get started with the lecture here. Last time we started this chapter focus on sound. So basically sound is also a wave. It's a mechanical wave, okay? And then our hearing is this perception of the sound. As sound is a wave, so then we can also use this these quantities to describe sound. So the frequency, the wavelength, and then the period, okay? And then the speed of the wave can be determined by these quantities. It could be either the wavelength times the divided by the period, or wavelength times the frequency. Sound travels with different speeds in different materials. So in air, it's actually travel slower than in liquid or in metal. Okay, so it also depends on temperature. The higher the temperature, the faster the speed of the sound in media. Okay, and then if you are having different types of gases, it's also having different speed. Okay, so it's inversely proportional to the mass of each of the molecules, the gas molecules. All right. Today we'll be talking about the sound intensity and sound level, and then also the Doppler effect. Okay, so let's take a look on the sound intensity. So we mentioned this in chapter 16. The intensity is defined as the energy passed through a given area divided by time t. Okay, so then EI as the symbol for intensity is equal to E, the energy divided by A, area divided by time t. And then use the definition for power equals to energy divided by time t, so the intensity is equal to power divided by area. Okay, if you have a point source, okay, then the intensity at the distance r away from the point source is going to be P divided by 4 pi r squared, because the area is going to be the spherical area. Okay, it's the sphere of the the area of the sphere with radius r. So the way our ear works when we hear sound, okay, so it's not directly proportional to the intensity we receive, okay, but it's actually proportional to the logarithm of the intensity, okay. So intensity level, that's what we hear. If we hear something like twice as loud, it doesn't mean the intensity is twice as much, but it's actually 10 times as much. Okay, so then we call it the intensity level beta. Okay, the symbol beta represent intensity level. It's equal to 10 dB, dB which is the unit for intensity level called decibel, times logarithm of the intensity I divided by the intensity 0, which is the threshold of the sound that we can hear. Okay, so that's the faintest sound we can hear with an intensity of I0. That is equal to, actually a very small number, 10 to the negative 12 watts per meter square. Okay, so intensity level again would have a SI unit as decibel, which is dimensionless, just like angle has SI unit of radian, which is also dimensionless. Okay, All right, so this is the equation you would use to calculate intensity level. So beta equals to intensity level, beta equals to 10 times logarithm of I divided by I naught. Okay, I naught is this constant number listed down here. Okay, so here is the range of the intensity levels that we can hear. Okay, so it's basically pretty much from anything from 0 to 120 decibels. Okay, anything larger than 120 decibel that will do damage to our ears. Okay, so in a typical classroom, it's about 50 decibel. If someone is whispering, it's about 20 decibel. Okay, so that's how much intensity level that is according to some of the sound we hear regularly. Okay, so let's take a look one example here quickly, an easy one, and then we'll take a second look on the second one. Okay, so this one says a crying child emits sound with an intensity level of 8.0 times 10 to the negative 6, that is in watts per meter square. Okay, so it says find the intensity level of the child's sound in decibel. Okay, so then we'll be just applying the equation we just checked in the previous slide. Okay, so I'm pretty much familiar with the crying sound from the kids because we have two little ones at home. One is only 13 months old now. The other one is 3-year-old. The 3-year-old still cries a lot these days. Okay, but let's take a look. Okay, so to calculate the intensity level, we use this equation. So intensity level beta equals to 10 dB decibel, the units, times logarithm of the I divided by I naught. Okay, where I naught is this 10 to the negative 12 watts per meter square. Okay, it's given I as 8.0 times 10 to the minus 6 watts per meter square. So pretty much you just plug in those two numbers in this equation. So 10 dB times logarithm of, okay, 8.0 times 10 to the minus 6 divided by 10 times 10 to the minus 12, or 10 to the negative 12. Okay, they're having the same units, watts of per meter square. Okay, so then plug in the numbers in your calculator, you'll get this as 69 decibel. Okay, so it's louder than the noise in a classroom typically. All right, and then sometimes two of our kids will cry at the same time, so that's even louder. But let's take a look how much louder is that in terms of the intensity level. Okay, so part B says if the intensity level for this child and its twin both crying with identical intensities. All right, so then the new intensity level, let's call it beta prime, should be equal to, again, this equation 10 dB times the logarithm of the I. Okay, this time let's call it I prime, still divided by I0. Okay, so I prime, because there are two children with the same intensity sound in sound, so then we should do 2 times. Okay, so it's 2 times. I should do 2 times 8.0 times 10 to the minus 6. Okay, so then we plug this number in the place of the original I intensity. Okay, so then this is 10 dB log of 2 times 8 times 10 to the minus 6 watts per meter square divided by 10 to the negative 12 watt per meter square. Okay, so if you plug in all these numbers in your calculator again, then you'll realize that it's beta prime is not going to be twice of beta, but it's going to be 72 dB decibel. Okay, so about if the intensity increase about doubles, okay, intensity doubles, then the increase in intensity level is by 3 decibel. Okay, it's not by 2 times. Okay, so it's by only by 3. All right. So this is the first example on intensity level. All right. So it's I think it's kind of pretty straightforward. You just use this equation of beta equals to 10 dB log of I divided by I0. Okay. All right. Any questions you guys might have? Just unmute yourself. Okay, and then let me know. All right. Again, if you haven't sent me a text in the chat, send it in the chat so I can take your attendance later from there. Okay, so if you haven't say hi or good morning or whatever in the chat, just typing anything there, and I'll take it as attendance later. All right. So now let's take a look on the second example here on intensity level. Okay, so this one says the residents of Hawaii, they are warned of approach of a tsunami by sirens mounted on the tops of towers. Suppose a siren produces a sound that has an intensity level of 120 decibel at a distance of 2 meters. Treating the siren as a point source of sound and ignoring reflections and absorptions, find the intensity level heard by an observer at the distance of 12 meters and 21 meters from the siren, and then how far away can the siren be heard. Okay, so let's take a look here. You guys can take a look on the problem itself, and then we'll take a look at the solution together in just a couple of seconds. Okay. All right, so let's take a look here. So on this one, it tells us the intensity level beta is equal to 120 dB when R is equal to 2.0 meters. Okay, now it says we can treat the siren as a point source. So then the power or the intensity, okay, of the siren at distance R, which should be equal to power divided by 4 pi R square. Okay, and intensity level beta can be calculated according to 10 dB logarithm of I over 10 to the minus 12. Okay, this is I naught. Okay, meter square. Okay, so these are the informations we know. Okay, so given that we can find the intensity or the power of the siren, okay, because intensity can be calculated by this. Okay, if beta is equal to 120, then intensity at 2 can be calculated. All right, at R equals to 2. So then we can calculate the power. With that power, we can calculate the power at different locations, 12 meters and 21 meters. Okay, and then we can plug it back into this equation. We can get the intensity level at 12 meters and 21 meters. Okay, so let's take a look here. So on A here, so we can set this up 120 dB, that is the intensity level that an observer can hear at R equals to 2. Okay, so then we can calculate here what's the intensity here. All right, now you guys probably want to practice this yourself after class or follow the instructions here on how to deal with log. Okay, so here 10 and 120 will cancel out, so you'll have 12 remaining here. Okay, so then to solve for I here, you want to do 10 to the power of both sides. Okay, so that means 10 to the 12 should be equal to 10 to the log of that. So that will get rid of log. Okay, so on the left hand side, you'll have 10 to the 12. That should equal to 10 to the log. We'll get rid of log. Okay, so equals to I divided by 10 to the minus 12. Okay, so this will tell you, or now at this point you want to multiply both sides by 10 to the negative 12. So 10 to the 12 and 10 to the negative 12 will cancel out. We'll leave 1 behind. So then intensity is going to be equal to just 1. Okay, or I is equal to 1 watt per meter square. Okay, that's your intensity at R equals to 2, so we can denote this as I2. Okay, so let's do it this way. That means the intensity at R equals to 2. All right, now I2 is equal to the power divided by 4 pi 2 meters square. Right, so then we can solve for this guy by setting I equals to 1. So 1 watts per meter square equals to P divided by 4 pi times 2 squared. Okay, so then this will tell you the intensity or the power by the siren that should be equal to, so this is 4 square or 2 square because becomes 4 times 4 becomes 16, so 16 pi. Okay, 16 pi will be the power of the siren. All right, so we have the power of the siren solved. So then we can use that to calculate intensity at different locations. Then use the intensity at different locations, we can calculate what's the intensity level at different locations. Okay. All right, so let's see. So the first one, part A, is asking you what will be the intensity level at 12 meters. So that means we need to find the intensity at 12 meters first. So let me write I12. That means the intensity at 12 meters. Okay, that should be equal to P divided by 4 pi times 12 meters square. Okay, so we have P as 16 pi watts divided by 4 pi. Okay, so I'm keeping the pi there instead of putting the numbers because I knew pi and pi down here will cancel out later. Okay, but it doesn't matter, even if you write any numbers, that will be fine. Okay, so times 12 meters square. Okay, so then this will give you, so you can see pi and pi will cancel out. Okay, this will give you 1 over 16 or 1 over 36 actually. I'm doing this in fraction, okay, but you guys can use the decimal numbers. Okay, so that's 1 over 36. Okay, so then you can use the intensity level equation here. So intensity level beta sub 12 means at 12 meters. Okay, should equal to 10 dB logarithm of I12 divided by I0. Okay, so 10 dB log of I12 is 1 over 36. I0 is 10 to the minus 12. Okay, so plug everything into your calculator, you will get 118 decibel. Okay, so it's 118 decibel at R equals to 12 meters away from the siren. All right. Similarly, for intensity level at 21 meter, you have to figure out what's the intensity at 21 meter first. Okay, so I sub 21 divided by 4 pi times 21 meters squared. Okay, again 16 pi watts divided by 4 pi times 21 meters squared. Okay, this will be so pi and pi will cancel out. 16 divided by 4 gives you 4. Okay, so it'll be 4 over 21 square. Okay, watts per meter square. Okay, you can put the numbers into a calculator and get the decimal digits there, but you can keep it there, okay? And then you can type in all the numbers at the end. So then beta 21 is equal to 10 dB log of I21 over I0, which is 10 dB log of 4 divided by 21 square, and then further divide by 10 to the minus 12, okay? So that will give you 99.6 decibel. Okay. Any questions you guys might have at this point so far? All right. If you have questions, just unmute yourself and you can ask. Okay. So the last one is asking you at what distance, how far away that the siren can be heard. What's the largest distance the siren can be heard, actually. So put it that way, okay? So that means at this distance, some distance away, some distance r away, okay? So I'm going to write I sub r. The intensity is going to reduce to the threshold, okay? So that means at that distance, is I is equal to I0, all right? Which I0 is equal to 10 to the minus 12, okay? Now, intensity is equal to power divided by 4 pi r squared. So that means we are looking for r here, with the intensity at that location to be 10 to the minus 12, okay? So then you get 10 to the minus 12 equals to P, which is 16 pi, okay, over 4 pi divided by r squared, okay? So again, this pi and pi will cancel out, 4 will cancel out 16 partially with 4 remaining, all right? So then your r squared here is going to be equal to the 4 divided by 10 to the negative 12, okay? Then this is 4 times 10 to the 12, all right? So r then will be equal to square root of this 4 times 10 to the 12, okay, which is 2 times 10 to the 6 meters. Okay, that should be in meters, all right? Yeah, I skipped the units because I know they are all in SI units, so I didn't put them here. So, but at the end, my answer should be in SI unit. For distance, it's meters. Okay, so that's the furthest distance that the siren can be heard. Of course, this is the scenario assuming that there's no reflection or absorption. Okay, so as the sound actually propagates in air, some amount of energy will be absorbed by the air, okay, and then some will be reflected by air molecules. So the actual distance that the siren can be heard should be much smaller than this guy. Okay, this is like 2 million meters away or 2,000 kilometers away. Okay, which is pretty far, but in reality, it shouldn't go that way. Okay. All right. So this thing is this one here. Let's pull this up so you can see the whole solutions for this problem. Okay, so that's our intensity level. Okay, so the key here is to get familiar with how to deal with log function. Okay, logarithm function here when you are solving the problem. All right. So if you guys don't have any questions, then we'll just move on to the next topic here in this chapter. Okay, so this is about this one is about the Doppler effect. Okay, so the Doppler effect is the change in pitch of a sound when the sound and the observers are moving. So either the source is moving or the observer is moving. Okay, or both. Then the pitch will change. Okay, so that means the frequency of the sound that the observer hear is different from the frequency that's given out by the source. Okay, so this is what we or you can put this in here. So let's imagine that the car here, okay, gives out a sound Okay, and then there's a stationary observer here. In the car is moving. Okay, so you can imagine the car gives out the sound, so in the form of waves. So then there will be the first waves comes out. Okay, that will reach the observer. Okay, a certain time t later, and then after a period, a capital T time, then there will be a second wave given out. Okay, or second wave peak given out by the car. At this point, the car has moved by a certain distance of the speed of the car times the period of the wave. Okay, so then for the second wave peak to reach the observer, it will take less distance to travel. Okay, to reach the observer. So then it takes less time. All right. So that means for the peaks to reach the observer, when the car is moving from peak to peak, okay, so the time it takes is smaller than if the car is not moving. Okay, so that means the period of the wave heard by the observer is getting smaller compared to if the car would be stationary. Okay, so if the period gets smaller, then the frequency gets higher. So then you hear higher pitch. Okay, so that's Doppler's effect. Okay, so you can prove it mathematically, or you can derive this equation mathematically. But we are not going to do this in the class here. But if you are interested, you can do it. Okay, but you can use your intuition that just I talked about in the previous slides. We can analyze the scenario. We realize that the frequency will get higher. Okay, as the source is approaching the observer. Okay, so then for the frequency heard by the observer here, so if you look at the second equation here, this is the one you are using. Okay, so you are using the frequency f by the observer. F sub o means the frequency heard by the observer. That should be equal to at the end. Okay, let's look at the very far end of this equation over here. Should be equal to 1 over 1 plus or minus us. That means the speed of the source. Okay, divided by v. This is the speed of the sound. Okay, this should be constant. Okay, if the media is not changing. So and then all this times f, the frequency gives out by the observer by the source f sub s. Okay, so if the observer is moving towards the if the source is moving towards the observer, you take the minus sign here. Okay, so if that's the case, all right, so you don't take both like plus or minus, but you take one of these signs. Okay, so for the negative sign, let me put this on this paper here so you can see it clearly. If observer is moving, or the source is moving, if source moving towards the observer, so then you take this equation f by observer, frequency heard by observer is equal to 1 over 1 minus speed of the source divided by the speed of the sound times this frequency gives out by the sound. Okay, so you take this one, and then if the source is moving away from the observer, okay, so then you take this expression. Okay, you don't take positive and minus at the same time, but you pick one of them. Okay, so if source is moving away, then you take the positive sign in the denominator. Okay, if source is moving towards the observer, then you take the minus. Okay, so this one or that one. So you have to analyze the scenario, see which one applies here. Okay, so let's take the example here on this one here. So it says a bat moving with a speed of 3.25 meters per second and emitting sound of 35 kilohertz approaches a moth at rest on a tree trunk. What frequency is heard by the moth? Okay, and then B says if speed of the bat is increased as the frequency heard by the moth higher or lower, calculate that frequency given the new speed of the for the bed to be 4.25 meter per second. Okay, so let's take a look here. So in this case, we have a moving source. Okay, so then we are going to just take this equation or that equation. Okay, now in this scenario, the source is the bed. The bed is moving towards the mouse. Okay, so the source is moving towards the observer in this case. So we are going to take this equation on the top here. Okay, so we are going to use that one. So F0 is equal to 1 over 1 minus US over V times F by source. And we know that U by S, so U is the speed by the source, which is 3.25 meters per second here. For F by the source, the frequency gives out by the bed is equal to, this is given as 35.0 kilohertz. Okay. And then it says we should use, I didn't say here, but okay. So we should use the speed of sound, V, this is as 340 meters per second, okay? So that's a constant we can use, all right? Yeah, I forgot to put this in the, in the problem, but this is the number should be given, okay? I'll put that in later. So then here, everything is given. Okay, we can calculate the frequency heard by the mouse. So F0 equals to 1 over, okay, in the denominator, there's this big expression here, 1 minus 3.25 over 340. All right, whole thing here multiplied by 35.0 kilohertz. Okay, so then we get 35.3 in kilohertz. Okay, all right. So I'm expressing the answer in kilohertz, so I didn't have to put kilohertz into hertz, okay? But if you put into hertz, that's fine. All right. So B here is asking you what happens if the US is increasing. Okay, so then let's examine this equation over here. So if the speed U here, okay, U sub S increased, okay, then this term here increased. Okay, so 1 minus this guy will be then decreased. Okay, so the denominator, the whole denominator will be decreased. Then 1 over the denominator should be increasing. Okay, so we can analyze the scenario. So we will come to the conclusion that then if the U increase, then the pitch should be, the frequency should be increasing. Okay, or increases. It should increase. Okay, now let's verify our assumption here. So this time you'll just use US as the new number 4.25, okay, meters per second. Everything else remains the same. So let's see. F0 then equals to 1 over 1 minus 4.25 divided by 340. Okay, this whole thing together multiplied by 35 kilohertz. Okay, so if we punch all these numbers in your calculator, you'll figure this is going to be 35.4 kilohertz. Okay, so 35.4 compared to 35.3 increase, indeed it increased, okay, by a little bit. Okay. All right. Any questions you guys have? All right. So if not, then let me see. Let's move on here. So let's now look at a different scenario. So this time, if we examine the scenario that the observer is moving, okay, and then it could be the observer could be moving towards the source or away from the source. Okay, so let's take a look first when the observer is approach the source. Okay, so in this case again, the source will give out say wave peaks periodically. Okay, so or in distance like about lambda each time. Okay, so for the first wave front or wave peak to reach the observer, and then it gives out a second wave front or peak of wave a time t equals to the period of the wave later. Okay, so capital T later. So for the second wave to approach the observer, now again it will take a shorter distance because the observer now will moved by certain distance. Okay, so it's closer to the source. So then it takes less time to travel for the second peak. Okay, so you can see that from peak to peak, the time it takes for the wave to reach the observer, it gets smaller if the observer is approaching the source. Okay, so if the period gets smaller, then the frequency again increases. All right. On the other hand, if the observer is moving away from the source, okay, then it would take longer time because now the distance for the wavefront to travel from the source to the observer is getting larger and larger. Okay, so then the time it takes for consecutive wave peaks to reach the observer will get larger. So then period increase, so the frequency decreases. Okay, so again in this scenario, the pitch will change. Okay, if the observer is moving compared to the observer is stationary. All right. Again, you can do this mathematical derivation, but this is the result you'll be looking at. Okay, so you'll be looking at when using this expression here, either take the positive sign or negative sign. Okay, so then if the observer um, moves moving towards the source in this time, in this case scenario, okay, then the frequency heard by the observer now is different, so it's 1 plus mu observer divided by v, okay, times f source. Okay, so this is what you are going to take because the frequency will increase. Okay, so you take the 1 plus here. Now in the previous case you take the minus because this is in the denominator. Okay, so then the frequency will increase. All right, so pay attention to which equation you should be using. Now on the same case, if the observer moves away from the source, then the frequency you are going to take this expression 1 minus mu or u0 divided by vu. U0 is the speed of the observer times fs. Okay, so you are going to pick one of these two expression. All right, so let's take a look on an example here. It says when a bell in a clock tower rings with a sound of 475 hertz, a pigeon roosting in the belfry flies directly away from the bell. If the pigeon hears a frequency of 448 hertz, what's the speed? So in this case, the pigeon is the observer, and the bell in the tower is the source. Okay, the source is stationary. The observer is moving away from the source. Okay, so in this case, then you are going to pick the second expression here, or the second equation here. Okay, so this is what you are going to do. You are going to pick the second one here. So f0 equals to 1 minus u0 over v times fs. Okay, now you are given this as 440, or actually, this is given, the pigeon hears this frequency, so that's fo, so 448 hertz equals to 1 minus, okay, u0 divided by, because the bell gives out sound, so that's the speed of sound should be 340, okay, times the frequency gives out by the bell 475 hertz. Okay, so then we are looking for mu 0, the speed of the observer of the pigeon here. Okay, so what you want to do is divide both sides by 475. Okay, then you get that. Okay, equals to 1 minus that guy. Okay, so you guys can do the algebra here by yourself. I'm going to just skip a couple of algebras. Okay, so at the end you can solve this for your u0 as 19.3 meters per second. Again, I didn't put the speed of sound, but it's a constant here, so that should be 340, okay, meters per second. All right. Questions you guys might have? All right, so let's move on then. Now, more often in general, you could have this source is moving, and then at the same time, the observer is moving as well. Okay, so then you are going to combine the two scenarios we mentioned earlier. So then in the combination, then this is the expression you'll be taking. Okay, so f of the heard by the observer is going to be equal to speed of sound in air. This v is the 340 typically, plus and minus u of observer, okay, and then divide by v, again the 340, plus minus u of the source, okay, and then times the frequency of the source, okay, and then you'll be taking the same rules as we mentioned earlier, okay. So when the observer is moving, so then you are taking take a look on the top here. So if the observer is moving away, then you take the minus sign here. Okay, if the observer is moving towards the source, you take the plus sign here. On the other hand, if the source is moving away from the observer, then you are going to take the positive sign. Okay, all right, and then when the source is moving towards the observer, you are going to take the minus sign. Okay, so these two are different. Okay, so observer, so when the observer is moving away, you take the positive in the you take the minus in the numerator. When the observer is moving towards the source, you take the positive. On the other hand, it's the opposite. Okay, so when the source is moving towards this observer, you take the minus sign. When the source is moving away from the observer, you take the positive sign. Okay, so be careful about the positive and negative here. All right. Now, also Doppler's effect has other applications as well. Okay, so it has like the weather radar, speed radar by the police. Okay, so if you guys are ever been caught by police man for speeding, then it's likely they use a speed radar. Okay, so I had one experience myself when I moved to Ohio, and that's the only chance that I was being caught by speeding here. I usually don't speed, but I was like a little bit higher. I was like driving at 67 on a speed limit of 55. That day, particular day, I was caught. I was, although I was following the traffic, but I didn't pay attention to my speed. So they use speed radar. Okay, so that's Doppler's effect. Okay, being used. All right, and then you can also Doppler's effect can be also applied to other waves, like say EM waves. Okay, so that's the astronomical measurement, the how people determine how fast is the particular say galaxy is moving away from us. Okay, that's the by application of Doppler's effect. Okay, so if you look at the expression earlier, so say let me put this up here. Okay, so if you look at this one of these expressions, especially when you are looking at this one here, okay, if the source is moving towards the observer, okay, at certain point, if the source is moving very fast close to this, the speed of source is close to the speed of sound, okay, then you can see then the frequency of the observer will increase very much, because pretty much the denominator becomes 0. Okay, so 1 over 0 is going to be an infinity large number. Okay, so then the frequency will skyrocketing, as the curve shows here in yellow here. Okay, so that goes up very quickly. Okay, so if that happens, you will hear very high pitch of the sound, and then the intensity of the sound will be very large as well. That's called sonic boom. Okay, so if an aircraft is traveling at speed of sound, then you'll see very loud noise. Okay, That's called sonic boom. All right, now let's take a look example on the combination of the two scenarios when both the observer and the source, they are moving at the same time. Okay, so here it says a motorcycle and a police car are moving towards each other. So the police car gives out a frequency, sound of frequency of 523 hertz, and then has speed of 32.2 meters per second. Motorcycle has a speed of 14.8 meters per second. What frequency does motorcyclist heard here? Okay, so in this one, you are going to take this expression f by the observer equals to v speed of sound plus minus u0, u of observer, divided by v plus minus u of the source times the frequency by the source. Okay, now we are going to determine if we are going to pick a positive sign here or negative here. So because they are moving towards each other, so that means the source is moving towards the observer, and then observer is moving towards the source. Okay, so in the numerator, you are going to pick the positive sign. Okay, and then in the numerator here, you are going to take the negative sign. Okay, so then you are going to take f0 equals to u plus v plus u0, v minus us. Okay, it's u at u o on top, us at the bottom, times fs. Okay, so take 340 again here, plus 14.8 divided by 340 minus 32.2. Okay, multiply by the frequency gives out by the police car, 523. Okay, so then the frequency heard by the motorcycle is going to be 603 hertz. Okay, 603 hertz here. Okay, so yeah, you guys will get some practice in the homework assignment on how to pick which side. Okay, any questions you might have? Okay, so if not, then we'll check the rest of the sections here very quickly. So hearing, okay, so this is what the our ear look like. Okay, so so the sound will comes in as sound waves into the ear canals, and then we'll hit the eardrums. Okay, then there's all this like nerves and all these organs connect to the brain. Okay, which you guys know better than I do. Okay, because I'm not a biology major, but most of you guys have taken some biology classes. All right, so this is what happens. Okay, so then we can hear the sound. Okay, you can read this section more about how the ear works, but as I say, you guys probably know better than I do. Also on application of the sound wave, so for like say ultrasound, so yeah, so this is a picture of to see the babies in the mother's womb. Okay, so you can see it's basically from the ultrasound, so gives out and then it receives the echoes of the wave or the reflection of the waves back. Okay, and then you can see the images. All right. And then you can also use ultrasound to detect tumors. Okay, so this is also the medical applications. You guys can read them more. All right. And then this is a picture on how this will be working. Okay, so there's a transducer and a speaker and a microphone. Okay, so it gives out signal and then receive back signal. Okay. And then from the intensity that receive backward, you can actually process the signal and then gives out images. Okay. All right. So yeah, I guess that we'll finish this chapter here. Okay. So then next week we'll be checking on the optics, okay, geometry optics and wave optics, okay, and then hopefully we'll be able to finish that topic in the remaining 4 classes, okay. All right. Any questions you guys might have before we end today's lecture? All right. If you guys have no questions, then I'll see you guys on Monday. Okay, and then some of you guys in this afternoon for the lab. Okay, see you.